are comfortable with, know how to operate, all of this complacency that exists from decades of old technology, and pretend that doesn't exist, right? None of those dynamics exist. You've just got a new application, and you need to measure flow. Is there a one in your mind where Coriolis wouldn't be the best solution?
Yes, of course. And excuse me if I got into my sales talk too much. I'm still used to that. So you have to stop me at any time if you feel this is going into the wrong direction. And I'm not trying to sell any Coriolis to you, by the way. So yes, of course, there's applications where you just don't want to use a Coriolis, or you can't use a Coriolis. Okay. I was happy, and I still feel blessed that I was the one who introduced the world's first 4-tube Coriolis to the market, the Promas X. The Promas X was a true 14-inch device, or still is a 14-inch device, which is unmatched by, well, the 10 or 12-inch that we saw from Emerson. But it ends there. You can still put up a 16-inch flange to it. Maybe you can still put up a 20-inch flange to it. You can put two in parallel, so you maybe have enough capacity for going 32 inches, or what was it, 4,000, so that would be 8,200 barrels per hour. But then it stops. The technology simply is getting way too expensive, even with the progress in automation and everything, that you can put Coriolis mass flow meters in the real big pipelines. It doesn't work. So you would go naturally, you would go to ultrasonic flow meters, which you can put in up to, I don't know, 160 inches with clamp-on meters. So there's certain physical limitations to Coriolis that you should not neglect.
Okay, hold on. Explain that physical limitation again, Michael. I missed it.
The physical limitation is in the line size, in the diameter of your pipe.
Okay, got it.
So
as it gets too
ultrasonic.
Large.
Yeah.
So what I'm hearing is Coriolis, or some sort of extremely high quality, highly accurate flow technology that can account for all kinds of changes in conditions. Those all make sense in applications where there's a great deal of variability, there's a high cost of inaccuracy, and the line size is smaller than a particular amount. Is that
correct?
A way to think about it?
Yes.
Okay, so can you just give us some examples of what applications fall into that sweet spot, and then most importantly, which ones fall outside of it, where it's just like, yeah, you'd be wasting money on a Cadillac.
True. You better off with the Volkswagen. Okay, so anything sweet spotty is very low flow. Like we're talking really small Coriolis meters, like 0.3 millimeter line diameter. That's something that you can do with the Coriolis, but not with the rest. And that's not so uncommon. If you think about dosing of pheromones, if you think about dosing of aroma, dosing of different gases, that's our Coriolis. And the good thing about Coriolis is it can measure liquids, it can measure gases, it can basically, you get it in one pipe, 2-pipe design, straight pipe, whatever it is. It's quite universal in this line between 0.3 millimeter diameter and let's say 14 or 16 inch diameter.
Okay.
If you want to measure mass in general, you are bound to use Coriolis or thermal. Any of the others, electromagnetic, ultrasonic, vortex, differential pressure, all of the mechanical ones, all of them only measure volume.
Okay. Yeah, all right. I guess we're trying to understand targeting here, Michael. What are presumably the more complex applications that have high variability, changes in phase, high